Welcome, friends. I'm glad you're here today. Let's descend together in thought through 4,000 miles of rock and metal to uncover the hidden layers, swirling currents, and ancient secrets at Earth's core. If you enjoy these quiet journeys of discovery, please like, subscribe, or share. Thank you. The planet wears a skin of stone that seems solid, but it thins and frays like cooled glass along the edges of great plates, a brittle rind floating on deeper motion. This crust, scarcely 5 to 10 kilometers thick beneath most oceans and roughly 30 to 70 beneath many continents, carries mountains, rivers, and coasts, while remaining the most delicate layer of the interior. Oceanic crust forms where mantle melts and basalt chills quickly at spreading ridges. Continental crust accumulates by slower amalgamation of buoyant silica-rich melts that rise from depth. Basalt spreads in thin sheets along the seafloor, gabbro crystallizes beneath it, and together they make a layered oceanic floor that rides outward on conveyor belts of lithosphere. Granite bodies cool slowly in continental roots, knitting feldspar and quartz into mosaics that later stand high when erosion removes their cover. The surface looks still, yet the crust moves a few centimeters each year, drawn and pushed by mantle flow and the pull of sinking slabs, and the motion rearranges coastlines close as seas and lifts mountain belts in timescales longer than language. Seismic waves map this thin shell with clarity. Compressional waves speed up as they cross dense coherent rock, and shear waves fade when they meet melt. A sharp change in wave speed marks the Mohorovicic discontinuity, the boundary between crust and mantle. It sits shallow beneath the oceans and deeper beneath continents, but its nature varies from textbook ideal to complex transitional zones. Heat leaks upward through this shell from two sources: the planet's stored formation heat and the steady decay of uranium, thorium, and potassium, and the contrast between cooling above and heating below helps set plates in motion. A lesser-known detail hums constantly within the stone. Even on clear days without storms, the solid earth vibrates with microseisms, triggered by the push and pull of ocean waves colliding in deep water and along continental margins. Seismometers write this faint music as a steady band of energy, a planetary murmur that threads through sand, clay, basalt, and granite, as if water and rock share a private rhythm. Soft ironies collect on this surface. The thinnest layer carries the tallest mountains, a lace of brittle rock holding peaks that press into the cold upper air. The crust that looks permanent renews itself incessantly as ocean basins open and close, so that the youngest stone lies under the deepest water while the oldest buoyant continents drift above it. The rocks that seem heavy with their dark hues are the ones that sink, while the paler, more silica-rich granites float like rafts. Where two plates meet, one can plunge beneath another and draw the ocean floor downward into trenches, folding sediments into accretionary wedges and feeding arcs of volcanoes that outline the margins of seas. Elsewhere, continents slide past each other and knit scarps across deserts and cities. Transform faults bruise the crust without swallowing or creating much of it. Water ice and air sculpt the crust, and isostasy lifts roots as mass erodes, so a mountain can rise taller even as its summit is worn. Rivers comb feldspar into clay glaciers, grind crystalline rock into flour, and the sea sorts grains into beaches that glitter and then sink into new strata. A basalt pillow forms at a ridge, cools with a glassy skin, and is buried under more pillows. Far away rain beats on granite slabs, and dark varnish of manganese and iron blooms slowly in arid light. The crust archives all of this with selective generosity, keeping a layer here, dissolving another there, turning most stories into fragments. A quiet mystery shadows this mapping. How and when did continental crust accumulate its present volume, And what did the earliest crust look like before subduction learned to erase records so efficiently? Some lines of evidence point to rapid early growth under a hotter mantle. Others trace a steadier rise through prolonged recycling and differentiation. The evidence is partial because plates consume their own pages. Another uncertainty sits at the crust-mantle boundary itself. In some places, the Mohorovičić discontinuity marks a frozen magma. Cumulate in others, a metamorphic change in chemistry and texture, and in still others it appears blurred by serpentinization, or melt a shifting threshold rather than a single sharp plane. A quiet analogy helps the scene settle. The crust behaves like the cooling skin on a pot of molten metal, firm enough to carry its own weight, yet cracked and mended continually as heat moves from below. Like that skin, the crust thickens in cold places and thins where heat rises, and the stresses that gather along its seams drive motion far from their source. The same physics that hardens glass under cold and softens wax under warmth plays out in crystalline lattices here, so rock that seems rigid. In a hand sample flows imperceptibly over long intervals, while rock that seems viscous shatters in an instant under sudden strain. Time marks the layers unevenly. Almost all oceanic crust is younger than 200 million years swept clean by subduction, while continental interiors preserve rocks older than 3 billion years. Some tiny zircons date to more than 4 billion years, crystals older than any known rock body carried again and again through cycles of weathering and redeposition, until they lodged in younger sandstone. Their endurance contrasts with the fate of entire ocean basins that come and go without leaving more than a line of metamorphic rock at the edge of a craton. Seismic tomography now renders the crust and uppermost mantle as volumes of variable speed, a slow lattice in which cold slabs descend and warm upwellings rise, and the crust rides these currents while also shaping them through its distribution of mass. Through all of this, the skin of stone keeps its paradoxical grace. It is thin, and it carries everything. It is fragile, and it bears mountain ranges that scrape the cold upper air. It looks permanent, and it is continuously replaced by firewater and the slow pressure of moving plates. Heat rises from deeper layers, pressure tightens grain boundaries. Seismic waves race outward from distant earthquakes and sketch depth as if with one slow pencil, and the crust holds its place at the meeting of light and liquid and stone, the boundary where weather meets rock and rock remembers weather. The path inward begins here on a surface that is both archive and threshold, and the long descent through pressure, heat, and metal waits beneath this thin, busy calm. Beneath the plates lies the lithosphere, a rigid shell of crust and uppermost mantle, fused into slow-moving rafts that drift over a warmer, weaker layer. This shell extends perhaps 100 kilometers beneath continents, and less beneath oceans, thickening with age as it cools and stiffens. It moves as a unit in response to forces both subtle and immense. The slow drag of mantle convection from below, the sinking weight of slabs, pulled into trenches, and the gentle push of magma rising at ridges. The lithosphere is not uniform. Some sections are ancient continental keels, cool and buoyant, resisting subduction for billions of years, while others are young oceanic slabs, dense and ready to sink back into the mantle. Beneath its base lies the asthenosphere, a region of rock warm enough to deform over long periods where seismic waves slow slightly, and partial melt may collect in films along grain boundaries. It is here that plates decouple from deeper flow sliding at rates measured in centimeters per year, a pace invisible to human life, yet enough to open and close oceans in geological time. The boundaries between plates are drawn in fault lines, ridges and trenches, their shapes marked by earthquakes, volcanoes and chains of mountains. A lesser-known detail hides in the quiet spaces between even the interiors of plates. Far from boundaries carry the scars of old rifts, sutures and faults, relics of past collisions and separations. These ancient features can focus seismic energy, or guide the movement of fluids deep underground long after the events that formed them have faded from memory. Soft ironies settle in the mechanics of this layer. The lithosphere, though strong, can break suddenly under stress that built for centuries, releasing in seconds energy that reshapes landscapes. The plates that seem to float independently are locked in a global network, so the push in one place is felt as a pull in another. The coldest, most rigid slabs end their journey by descending into the hottest depths, carrying surface rock into zones where minerals are remade. The base of the lithosphere is a gradual transition rather than a sharp surface, and its depth can vary with temperature composition and the history of stretching or thickening. In places where mantle plumes rise, such as under volcanic hotspots, the lithosphere thins and warms, sometimes cracking to let basaltic magma ascend to the surface. Elsewhere in stable continental interiors, the lithosphere grows so thick that its keels deflect mantle, flow-casting shadows of slow seismic waves far downstream. Seismology through the travel times of compressional and shear waves reveals the boundaries of this shell. Earthquake waves bend and reflect at its base, and the differences in speed between cool, coherent lithosphere and warmer asthenosphere below sketch an image of a planet wrapped in armor that moves. Heat transfer here is mostly conductive, creeping through solid rock, rather than surging in convection, so the temperature rises steadily with depth until it meets the more mobile currents beneath. The quiet mystery lies in the history of lithospheric assembly. How did ancient cratons achieve such stability that they have survived intact for over 2.5 billion years, while younger lithosphere is continually recycled? Some models suggest rapid thickening during hotter, more active tectonic cycles in the early Earth, but the precise combination of pressure, temperature, and composition that makes lithosphere so resilient remains unresolved. Another uncertainty rests in the fine-scale structure of the lithosphere-asthenosphere boundary. In some regions, geophysical surveys detect a sharp seismic drop consistent with partial melt. In others, the change is gradual, suggesting only a shift in grain alignment or water content. A gentle analogy emerges from slow observation. The lithosphere moves like an immense cracked sheet of pack ice drifting over the ocean. Its edges collide, slide past, or separate, and the patterns of pressure beneath influence the speed and direction of motion. Just as sea ice grows thicker in cold regions and thins in warmer currents, lithosphere thickens where heat is low and thins where heat rises. The difference is in the scale of time. Where ice can change in days or weeks, lithosphere changes over millions of years. Even within its rigidity, the lithosphere contains faults and shear zones that can reactivate after long dormancy. A fault buried beneath sediment in a quiet plain may have once been the edge of a vanished ocean, and with enough strain it can move again, shaking cities far from active plate boundaries. Gravity anomalies trace these hidden scars, subtle variations in density, mapping the old architecture of plates. In mountain belts, the lithosphere can double in thickness as crust piles up, and mantle lithosphere root deepens. In rift zones, it can thin to half its average, letting the asthenosphere well up and melt. The stability of ancient continental interiors depends on the buoyancy of their thick, cool roots, which resist subduction even as plates shift around them. These cratonic keels extend deep enough to influence mantle flow, diverting convection cells and affecting patterns of upwelling thousands of kilometers away. Geochemists study xenoliths, fragments of mantle rock carried to the surface in volcanic eruptions that record the conditions at the base of the lithosphere. Peridotites from stable cratons show depletion in basalt-forming elements, evidence of ancient melting that left the residue buoyant and refractory. The surface world rests on these deep structures without sensing them, though their slow rearrangements have shaped continents, oceans, and climate for hundreds of millions of years. Through the lens of geological time, the lithosphere is not static but part of a cycle of creation, movement, and destruction. New lithosphere forms at ridges where basalt wells up, cools, and spreads. Old lithosphere sinks into trenches where it is pulled by its own weight into the mantle, its minerals transformed under increasing pressure and temperature. The balance between creation and destruction maintains the planet's surface area, while recycling material between deep and shallow realms. Over billions of years, this process has regulated the composition of the atmosphere, and oceans influenced the distribution of life and left an irregular record in the rocks. Even the most stable regions have seen change, ancient mountain belts worn to stumps, old faults healed by mineral growth, and rifts that opened only to close again. In quiet moments, seismic stations record faint signals from distant earthquakes passing through the lithosphere, their paths bending and splitting as they cross its varied structure. These signals reveal not only the present state of the plates, but also the deep memory of their past. Beneath its apparent solidity, the lithosphere is a record of emotion frozen into stone, the bridge between the brittle surface and the slow currents of the mantle below, and the first step into the planet's deeper, hotter interior. The mantle's slow currents begin far below the rigid lithosphere in rock that is solid, yet moves over time as if it were an immense and heavy fluid. Composed mainly of silicate minerals rich in magnesium and iron, the mantle extends from the base of the crust to a depth of about 2,900 kilometers, wrapping around the core in a thick shell. Although the temperature here ranges from roughly 500 degrees Celsius near the top to more than 4,000 near the base, the immense pressure keeps the rock mostly solid. Movement occurs through creep, as crystals deform and grains slide past each other at rates too slow for the eye to perceive. These convective flows are the planet's deep breathing, drawing heat from the interior toward the surface and recycling material between depths and heights. The flows rise in broad, slow upwellings and sink in cooler, denser slabs that were once ocean floor. A basaltic plate can dive into the mantle and descend for thousands of kilometers before merging with the surrounding rock, its minerals changing as pressure and temperature increase. Convection cells are not perfectly symmetrical or steady. They shift in response to surface events and changes deep below, linking the fate of continents to the quiet circulation of the mantle. A lesser-known detail within this vast layer is that seismic waves do not travel evenly through it. Regions of hotter, less dense rock slow the waves, while colder, denser material speeds them, creating a mottled map of the planet's internal temperature and composition. Some of these patterns reveal the presence of long, ribbon-like slabs of subducted lithosphere still sinking toward the lower mantle, while others show the broad columns of warmer rock that may feed volcanic hotspots. Soft ironies are found in this movement. Rock that is far hotter than any lava on the surface moves more slowly than a fingernail grows. The same currents that slowly lift continents can also lower them depending on where the flow passes. The process that drives volcanic islands into existence also recycles them into the deep mantle. At the boundaries between the upper and lower mantle, minerals such as olivine transform into denser forms, changing their crystal structure to adapt to the increasing pressure. At about 410 kilometers depth, olivine becomes wadsleyite and deeper still. At about 520 kilometers, wadsleyite changes to ringwoodite, each transformation marked by a change in seismic velocity. The mantle's convection is influenced by these phase transitions, as the density changes can either speed or stall the movement of rock. Some models suggest that slabs can temporarily rest at these depths before sinking further, while plumes may hesitate before rising past them. The quiet mystery lies in the exact pattern and vigour of mantle convection. Is the mantle stirred in separate layers with the upper and lower parts exchanging little material, or is it a single system reaching from crust to core? Seismic tomography and geochemical tracers offer partial answers, yet the deep paths of material remain imperfectly known. Another uncertainty involves the role of water in mantle dynamics. While liquid water cannot survive at these depths, hydrogen atoms bound in mineral structures may influence melting viscosity and the speed of convection. Ringwoodite samples from deep within the mantle have been found to contain significant water content in their crystal lattices, hinting at vast reservoirs locked away far beneath the surface. A gentle analogy can help bring this hidden process closer to thought. The mantle behaves like a vast slow pot of thick syrup, heated from below and cooled from above with rising swirls and sinking threads. Yet unlike any kitchen vessel, the mantle's currents span thousands of kilometres, take millions of years to complete a cycle, and move through rock that would shatter if handled at the surface. Even in its motion, the mantle records its history. Chemical differences between mantle regions tell of ancient subduction, primordial reservoirs left from the planet's formation, and the steady reshaping of its interior by plate tectonics. Volcanic rocks at the surface carry isotopic signatures that trace their source to specific depths, allowing geologists to identify whether the magma came from a depleted mantle region, rich in prior melting, or from a less disturbed reservoir deep below. Some volcanic chains, such as those forming over mantle plumes, produce lava with signatures that suggest material rising from near the core mantle boundary, a journey of thousands of kilometres. The mantle's role in the planet's life is constant and understated. It is the engine that drives the movement of plates, the source of nearly all volcanic material, and a major control on the long-term carbon cycle, which helps regulate climate over geological time. Through subduction, carbon-bearing sediments and altered oceanic crust are drawn into the mantle. Through volcanic eruptions, some of that carbon is returned to the atmosphere. The cycle operates so slowly that entire mountain ranges can rise and erode, while it turns only a fraction of a revolution. The mantle also interacts with the surface in more immediate ways during large eruptions or earthquake-generating shifts in plates. Yet even these events are only the visible ripples of the deeper flow. Its patterns are far larger than human history and far steadier than surface storms. In certain locations, seismic studies have revealed large, low-shear velocity provinces at the base of the mantle, vast regions where shear waves slow markedly. These zones may be hotter, chemically distinct or partially molten, and they appear to influence where mantle plumes rise. Their true nature remains uncertain, and their stability over time is an open question in geophysics. Despite its scale and influence, the mantle exists entirely out of direct reach. All knowledge of it comes from indirect evidence, seismic waves, high-pressure experiments, the chemistry of erupted rocks, and theoretical models tested by computer simulations. Each method offers only a partial view, and together they form an image that is still incomplete. The slow churn of silicate rock, the transformation of minerals under immense pressure, the recycling of the planet's outer shell, and the storage of heat from both formation and radioactive decay, these define the mantle's existence. It is not empty space, not molten ocean, but a slow, dense tide that has moved without pause for billions of years, shaping the surface world while remaining hidden beneath it. Here the journey inward lingers among currents that no eye can see, swells of stone rising and falling over spans of time too vast to measure the deep and constant motion that steadies the restless crust above. Frozen in motion, the minerals of the upper mantle keep an archive of the planet's past magnetic fields, aligning their microscopic structures with the invisible lines of force that thread from pole to pole. When molten rock rises toward the surface and begins to cool, iron-bearing minerals within it can lock in the direction and strength of the magnetic field at that moment in time. This record is called remanent magnetization, and it is preserved in rocks both at the surface and deep in the mantle lithosphere, where they have been carried by tectonic motion. In the upper mantle, especially near mid-ocean ridges, new oceanic crust is formed from basaltic magma, and as it cools through the Curie temperature of magnetite, it acquires a permanent magnetic signature. As plates move away from these ridges, the polarity of this magnetization alternates in wide, symmetrical stripes on either side, reflecting the periodic reversals of Earth's magnetic field over hundreds of thousands of years. These magnetic stripes on the seafloor are a visible expression of a process that is also recorded invisibly in mantle rocks that never see daylight. A lesser-known detail is that peridotite xenoliths brought up from the mantle in volcanic eruptions sometimes preserve the same paleomagnetic signals as surface rocks, suggesting that even portions of the mantle lithosphere have been imprinted with the orientation of ancient fields. This silent record extends far beyond human history, capturing not just reversals, but also subtle variations in field strength and wandering of the poles over millions of years. Soft ironies exist in this magnetic memory. The rocks that store it were once molten and entirely unaligned, and only through cooling into rigidity did they become witnesses to invisible forces. The very patterns that seem static today record a field that is always changing. Even as the deep mantle drives the dynamo that generates the magnetic field, its own minerals may be carrying memories of earlier configurations produced by the same process. Seismic tomography sometimes reveals zones of high velocity in the upper mantle remnants of old subducted slabs, which may also carry trapped magnetized minerals into deeper regions, burying magnetic history beyond the reach of surface observation. The process of locking in magnetic information is sensitive to temperature, composition, and deformation. If rocks are reheated above their blocking temperature, the magnetic record is erased or altered, a slow rewriting of history by the same forces that created it. The quiet mystery lies in how far down these magnetic imprints persist. Laboratory studies suggest that at great depths and high pressures, magnetic minerals may change their structure and lose their ability to preserve the field, yet the precise depth limit is uncertain. It is also unknown whether large-scale mantle circulation can carry magnetized rock into regions where it might remain stable for billions of years, or whether all deep records eventually fade. Another uncertainty is the exact mechanism by which some mantle minerals not typically considered strongly magnetic can hold weak but measurable remanent magnetization, hinting at minor inclusions or chemical alterations that enhance their capacity for memory. A gentle analogy helps to frame this archive. The mantle's magnetic record is like a palimpsest, a manuscript written upon many times with traces of earlier writing still visible beneath newer layers. Just as historians decipher faint ink to glimpse the past, geophysicists measure faint magnetic signals to reconstruct the drift of continents, the reversal of poles, and the evolution of the geodynamo. This memory is not uniform. Tectonic collisions can fold and tilt the recorded direction seafloor spreading, can create symmetrical but incomplete patterns, and mantle plumes can overprint older signals with new ones. Yet even with these disruptions, the overall coherence of the record allows the slow dance of continents and oceans to be traced back hundreds of millions of years. Magnetic anomalies on the ocean floor mapped with shipborne magnetometers were a key to confirming the theory of plate tectonics, revealing the orderly stripes that could only be explained by seafloor spreading and periodic field reversals. Those stripes are mirrored in the continental record, where lava flows of different ages show alternating polarity, and in some ancient cratonic rocks where stable remnants points to the positions of the magnetic poles, at times when the continents themselves were in different places. The interplay between the mantle and the magnetic field is ongoing. Heat flow from the mantle to the outer core influences the vigor of convection in the molten iron there, and in turn the patterns of that convection shape the field that mantle rocks will record when they cool. Over geological time, supercontinent cycles may affect the heat budget of the core, modulating the strength and stability of the field. In moments of reversal, when the field weakens and changes polarity, the magnetic archive records a more chaotic pattern, with multiple poles appearing and disappearing. These episodes are brief in geological terms, often lasting only a few thousand years, yet they leave a clear signal in the rocks that formed during them. The upper mantle's role in preserving magnetic history is indirect yet essential. Without the steady creation and destruction of oceanic lithosphere at spreading centers and subduction zones, the continuous record of field reversals would not exist. Without the stability of ancient continental lithosphere, some of the oldest magnetic signals would not have been retained. The mineral olivine dominant in the upper mantle is not strongly magnetic, but the accessory minerals within it, such as magnetite, ilmenite, and hematite, can carry remnant magnetization. In peridotite xenoliths, these minerals are sometimes found in microstructures that shield them from alteration, allowing the survival of ancient signals. The magnetic archive in the mantle is not an intentional record. It is an incidental one born of cooling mineralogy and the steady action of the geodynamo. Yet it has been essential in revealing the scale of planetary processes, from the drift of continents to the cycling of the field itself. In the stillness of deep time, the mantle holds these frozen moments, each a fragment of an unseen pattern that stretches from the core to the surface and beyond into the space where the magnetic field meets the solar wind. Here among crystals aligned to fields long gone, the journey downward pauses in a gallery of invisible lines, a museum without walls or light where the exhibits are grains of iron oxide, and the labels are written in the orientation of their atoms, marking the passage of the planet through its own shifting magnetism. Where rock flows, the mantle deep beneath the crust behaves in ways that seem contradictory to everyday experience. Composed largely of olivine and pyroxene with minor garnet or spinel depending on depth, it is solid by any direct measure, yet able to deform and move when pressure and temperature act over long spans of time. At depths between about 100 and 400 kilometers, where pressure is immense and temperatures are well above 1000 degrees Celsius, olivine grains begin to change shape without breaking, slipping along crystallographic planes in a process called dislocation creep. This is not the molten flow imagined in simple diagrams, but a slow rearrangement of the atomic lattice that allows rock to behave like an extremely viscous fluid. Convection cells in this part of the mantle may rise beneath spreading centers, feeding the continuous creation of oceanic crust or sink in the form of cooler slabs descending from subduction zones. In either case, movement is measured in centimeters per year, yet over millions of years these motions reshape. Continents generate mountain belts and close and open oceans. A lesser-known detail is that the viscosity of mantle rock here is not uniform but varies with grain-size water content and the presence of minor melts. Laboratory experiments and seismic studies suggest that even a tiny fraction of partial melt, perhaps less than 1% by volume, can reduce viscosity enough to influence the speed of flow. Water carried into the mantle by subducting slabs and bound within mineral structures can have a similar effect, lowering the temperature at which deformation becomes easier and allowing the rock to creep more readily. Soft ironies lie in the contrast between this deep flow and surface perception. Rocks that feel unyielding underfoot are in this context constantly in motion. The same material that supports mountains for millions of years can also stretch like warm resin under the right conditions. Movements that are imperceptible to human senses define the placement of every coastline and the height of every plateau. Seismic waves provide a partial map of these flows. Shear waves travel differently through regions of aligned crystals, revealing the orientation of mantle flow, while variations in speed show where temperatures are higher or lower than average. In some regions, the alignment of olivine crystals, known as lattice-preferred orientation, marks the direction of past and present deformation, like the grain of wood that records how a tree grew. These alignments can persist even after the flow has changed direction, offering clues to ancient mantle circulation patterns. The quiet mystery here is the scale and persistence of such patterns. Some seismic anisotropy suggests stable flow over tens of millions of years, while other regions appear to have shifted direction more recently. It is unclear how mantle convection reorganizes itself, whether gradually and predictably, or through sudden large-scale changes. Another uncertainty lies in the way small-scale heterogeneities in composition and temperature interact with large-scale flow, creating local eddies or channels within the broader circulation. A gentle analogy can help bridge the gap between human experience and this deep, slow world. The upper mantle behaves like a glacier turned on its side. Solid ice deforms under its own weight, flowing slowly downhill while carrying embedded rocks with it. In the mantle, solid silicate flows under the planet's heat engine, carrying fragments of lithosphere and traces of surface material deep into the interior. Just as crevasses open and close in a glacier, localized zones of strain in the mantle can create pathways for melt to rise or for minerals to realign. These zones are not fixed. They migrate, merge, or vanish as conditions change. The movement of rock here plays a critical role in the cycle of material between Earth's surface and its deep interior. Subduction carries oceanic lithosphere downward, where it heats, dehydrates, and undergoes metamorphic reactions, releasing fluids into the overlying mantle wedge and causing partial melting. This melting feeds volcanic arcs, returning material to the surface even as the rest of the slab continues its descent. Over time, the slab may penetrate into the lower mantle or stall at the transition zone, depending on its density and the viscosity of the surrounding rock. In the opposite direction, mantle plumes may rise from depths near the core mantle boundary, their buoyancy allowing them to pierce through the flowing rock above and deliver heat and material to the surface. The interaction between these upwellings and the moving upper mantle can create complex patterns of magmatism far from plate boundaries. Peridotite xenoliths brought to the surface in volcanic eruptions provide direct samples of this deep flow environment. Their textures reveal histories of deformation with elongated olivine grains aligned in consistent directions, evidence of steady shearing over long periods. Their mineral compositions record the depletion of basalt-forming elements during partial melting and the later enrichment from infiltrating melts. These chemical signatures offer a timeline of processes invisible to direct observation, linking the surface expressions of volcanism to the unseen circulation below. The rheology of the mantle or its flow behavior is a subject of intense study. Temperature, pressure, composition, and the presence of volatiles all interact to determine whether a region of rock resists movement or flows easily. Numerical models constrained by laboratory experiments and seismic data attempt to simulate this interplay, but the actual mantle is far more complex than any model can fully capture. Its structure is heterogeneous with patches of differing composition, variable grain sizes and networks of melt or fluid that may connect or disconnect over time. Despite these complexities, the overall flow of the mantle maintains the balance of plate tectonics drawing heat upward and recycling material downward in a cycle that has persisted for billions of years. It is a system in which the slow deformation of olivine grains, the subtle influence of trace water, and the vast scale of convection cells all combine to shape the planet's surface and sustain its geological activity. In the dim, crushing depths where rock flows like no fluid on the surface, the journey inward moves through a realm where time stretches, pressure mounts, and the boundaries between solid and liquid blur into a state that is both fixed and forever in motion. Heat from the beginning moves upward through the mantle, a combination of ancient warmth, left from the planet's violent birth, and the steady internal fire of radioactive decay. When Earth formed about 4.5 billion years ago, countless planetesimals and protoplanets collided, their kinetic energy transformed into heat that was trapped within the growing sphere. Some of that primordial heat remains slowly leaking away through the crust and ocean floor. Added to it is the continuous heat generated by the decay of long-lived isotopes of uranium, thorium, and potassium, whose atomic transformations release energy into the surrounding rock. Together, these sources sustain the temperature gradient that drives mantle convection, fuels volcanism, and powers the geodynamo in the liquid outer core. A lesser-known detail is that a significant portion of Earth's internal heat budget may also come from the slow crystallization of the inner core, a process that releases latent heat and drives compositional convection in the molten metal around it. Laboratory measurements and seismic models suggest that this freezing front grows only a fraction of a millimeter each year, yet over geological timescales the released energy is substantial. Soft ironies emerge in the behavior of this heat. The deeper the source, the slower it reaches the surface, so the warmth of the core may take hundreds of millions of years to arrive at the crust. The planet is steadily cooling, yet that cooling maintains the motions that keep its surface geologically alive. Heat itself moves by different paths: conduction through the lithosphere, convection in the mantle, and advection where molten rock rises through cracks or erupts at volcanoes. In the mantle, heat transfer is dominated by convection, where hotter, less dense rock rises and cooler, denser rock sinks, slowly stirring the deep interior. This stirring is far from uniform. Large stable structures such as cratonic roots and subducted slabs can redirect flow, creating regions where heat moves upward more efficiently and others where it lingers in place. The quiet mystery lies in the planet's heat budget. Exactly how much is left from formation, how much is generated today, and how these contributions have changed over time. Measurements from boreholes, ocean heat, flow surveys and satellite data give partial answers, but uncertainties remain about the distribution of radioactive elements in the deep mantle and core. Some geophysical models suggest that heat loss from the core has varied significantly through Earth's history, possibly influencing the longevity and stability of the magnetic field. Another unresolved question is whether mantle convection is becoming less vigorous as the planet cools and whether this might eventually slow plate tectonics. A gentle analogy helps to picture this deep warmth. Earth behaves like an immense iron kettle, heated not by a single flame but by embers embedded within its metal and stone. The embers cool slowly and their fading glow drives slow currents in the thick fluid of the mantle, just as uneven heating stirs liquid in a pot. Unlike any kettle, however, Earth loses heat mostly through the thin crust, and the pathways of escape are uneven, with mid-ocean ridges acting as great vents, while continental interiors release their heat reluctantly. The study of geothermal gradients, how temperature changes with depth, provides insight into this system. In stable continental regions, the gradient may be as low as 15 degrees Celsius per kilometre, while in tectonically active areas it can exceed 40 degrees. Such variations reflect both the heat flow from below and the thermal conductivity of the overlying rocks. In oceanic crust, the gradient is steepest near ridges, where magma is closest to the surface, and decreases as the crust ages and cools. Hydrothermal circulation through fractures in the seafloor can remove large amounts of heat, transporting it into the ocean and influencing global chemical cycles. This link between heat and water is another subtlety. Fluids circulating through hot rock not only move energy, but also dissolve and deposit minerals, altering the composition and strength of the crust. In subduction zones, water released from the descending slab lowers the melting point of the overlying mantle, wedge-producing magmas that rise to form volcanic arcs. Here, deep heat and surface processes meet directly, shaping landscapes and recycling material between Earth's outer shell and its depths. Volcanic activity offers a rare glimpse of heat's journey from origin to outlet. Basaltic lavas from mid-ocean ridges, andesitic magmas from volcanic arcs, and alkaline lavas from hotspots all carry chemical signatures of their source regions, telling of the temperatures and compositions where they began. Geochemists use these signatures to trace the movement of heat and material through the mantle, linking surface eruptions to deep convection patterns. Even the basalt that cools unnoticed at the ocean floor participates in this system, its crystallization releasing heat that has traveled upward for millions of years. The role of radioactive decay in sustaining this cycle is both constant and slow. Isotopes of uranium-238, uranium-235, thorium-232, and potassium-40 decay, with half-lives ranging from hundreds of millions to billions of years, ensuring that Earth's interior remains warm far into the future. Without this internal heating, the mantle would have cooled and stiffened long ago, shutting down plate tectonics and magnetic field generation. This interplay of primordial and radiogenic heat is the foundation of Earth's geodynamic vitality. In other words, the absence of one or both sources has led to geological dormancy. The Moon's small and poor in radioactive elements cooled quickly, and its surface has been static for billions of years. Mars retains some volcanic and tectonic features from a more active past, but its lower heat budget has left it largely still. Earth's sustained warmth is exceptional among rocky planets, a balance that has allowed ocean's atmosphere and life to persist over billions of years. Seismic studies sometimes hint at anomalies in heat distribution, such as ultra-low velocity zones near the core mantle boundary, that may represent hot, partially molten regions feeding mantle plumes. These structures remind us that heat flow is not smooth, but shaped by complex interactions between composition, phase changes, and convection. As the journey inward continues, the heat becomes not just a background condition, but the defining factor in the transformations of minerals, the movements of rock, and the generation of the magnetic field. Beneath the solid crust and lithosphere within the slow currents of the mantle, the warmth from the beginning still shapes the planet's present and its distant future, a legacy of formation that has not yet faded into silence. Mantle plumes rising from deep within the planet are narrow columns of hot rock that move upward through the surrounding mantle, carrying heat and material from depths that may approach the core mantle boundary. Unlike the broad, sluggish convection that circulates the upper mantle, these plumes are focused, buoyant upwellings that can punch through the overlying rock, thinning the lithosphere and triggering intense volcanic activity at the surface. In seismic tomography images, they appear as vertical or slightly tilted conduits of lower-than-average seismic velocity, indicating higher temperatures and, in some cases, partial melt. The most famous examples feed volcanic hotspots, such as those beneath Hawaii, Iceland, and Réunion, where chains of volcanoes mark the movement of tectonic plates over stationary plumes. A lesser-known detail is that the heads of these plumes, which spread out near the surface into broad mushroom-shaped structures, can be hundreds to thousands of kilometers across, while their narrow tails may extend for more than 2,000 kilometers into the deep mantle. When a plume head first reaches the lithosphere, it can produce vast outpourings of basalt known as large igneous provinces events that have occasionally coincided with mass extinctions and global climate shifts. The soft ironies of plume dynamics rest in their scale and persistence. The rising material moves no faster than fingernails grow, yet it can reshape continents and oceans over millions of years. Plumes that originate in the deepest mantle, where pressures exceed 130 gigapascals, may carry chemical signatures from parts of the planet untouched since its formation. The journey of a single plume from base to summit may last tens of millions of years, but its surface expression can fade in a geological instant if the supply is cut off or the lithosphere moves beyond its reach. Seismic studies reveal that some plumes may be rooted in large low-shear velocity provinces at the base of the mantle, vast regions with distinct composition or temperature that may act as plume nurseries. These provinces are themselves a quiet mystery. Their stability over billions of years and their role in mantle circulation are not yet fully understood. Another uncertainty lies in the relationship between plumes and plate tectonics. While plumes are often considered independent of plate boundaries, their arrival beneath rifts or subduction zones can interact with existing processes, intensifying magmatism or altering the course of tectonic events. A gentle analogy for a mantle plume is a candle flame in a still room sending a column of warm air upward. But unlike a flame, the plume is solid rock deforming and flowing under immense pressure, and the room in which it rises is itself in motion, slowly shifting the target where the plume reaches the surface. Over time, as the plate above moves, a plume can create a linear chain of volcanoes, each extinct in turn, as it drifts away from the heat source. The Hawaiian Emperor Seamount chain records such a path with a bend in its alignment, marking a change in the direction of Pacific plate motion about 50 million years ago. The chemical composition of plume-derived magmas often differs from that of mid-ocean ridge basalts, reflecting their deeper source. Higher concentrations of certain isotopes, such as helium-3, suggest that plumes tap into mantle reservoirs that have been isolated from the mixing of plate tectonics for much of Earth's history. These chemical fingerprints allow geochemists to trace plume material in surface rocks and sediments, linking eruptions to deep processes far beyond direct observation. The heads of plumes can also generate massive volcanic plateaus such as the Deccan Traps in India or the Siberian Traps in Russia, whose eruptions covered millions of square kilometers with thick basalt flows. These events release enormous amounts of gas into the atmosphere, potentially altering climate and ocean chemistry on a global scale. Although plume activity is often portrayed as steady, it can be episodic with pulses of increased upwelling or magmatism separated by long quiet intervals. The causes of these variations are not well understood. They may involve instabilities in the plume conduit interactions with surrounding mantle flow or changes in heat flux from the core. Even the initiation of a plume remains a subject of study. Some models suggest that plumes form when heat builds up beneath a thick insulating layer of mantle, eventually becoming buoyant enough to rise. Others propose that they originate at compositional boundaries, where differences in density focus upward motion. The base of the mantle is marked by a complex landscape of hot and cool regions, and plumes may emerge preferentially from its warmer, less dense zones. The surface expressions of plumes are more familiar volcanic islands, rift valleys and geothermal fields where heat escapes in concentrated form. Iceland sits astride a plume and a mid-ocean ridge combining the effects of both to produce one of the most volcanically active regions on the planet. In contrast, the Hawaiian plume lies far from any plate boundary, its volcanoes rising from deep ocean floor to pierce the sea surface. These settings differ in their tectonic context, but share a link to deep mantle upwelling that transcends the movement of plates. Plumes also contribute to the transfer of heat and material between Earth's deep interior and its surface, influencing the chemical evolution of the mantle over time. By bringing deep material upward, they introduce elements and isotopes that would otherwise remain locked away, enriching the upper mantle and crust. Conversely, subducted material may be drawn into the base of a plume, recycling surface-derived components back toward the core mantle boundary. The interplay between these vertical and horizontal motions adds complexity to the planet's internal circulation, making it a three-dimensional puzzle, whose pieces are still being assembled from scattered clues. In the stillness of deep-time mantle, plumes are persistent threads connecting the planet's heart to its skin, narrow yet powerful streams of rock that rise through darkness for millions of years before finding release in fire, steam, and stone. They are reminders that even in a world where most change is slow and hidden, there are focused forces that shape continents, build mountains in the sea, and alter the course of life at the surface. In continuing the descent inward, these vertical currents stand as markers of the deep mantle's vitality, signals that heat and motion reach every layer between the crust and the core. The transition zone lies between about 410 and 660 kilometers beneath the surface, a boundary region where the structure of minerals changes under the immense pressure and heat, and where vast reservoirs of water may be stored within crystal lattices. Here the familiar olivine of the upper mantle transforms first into wadsleyite, and then into ringwoodite, each with a denser crystal arrangement to withstand the rising pressure. These phase changes mark distinct seismic discontinuities. Waves travelling through the Earth speed up abruptly at these depths, allowing seismologists to detect the boundaries without ever seeing them. Laboratory experiments replicating the extreme conditions of the transition zone reveal that ringwoodite can hold significant amounts of hydroxyl within its crystal structure, the equivalent of several oceans' worth of water if distributed throughout the zone. This water is not liquid, but bound at the atomic level, influencing melting behavior, density, and the viscosity of surrounding rock. A lesser-known detail is that variations in the depth of these phase boundaries can reveal temperature differences in hotter regions. The transformations occur deeper, while in cooler regions they occur shallower. Subducting slabs descending through the transition zone can carry water deep into the mantle, in hydrated minerals releasing it during these phase changes, and affecting the dynamics of melting above. Soft ironies shape the perception of this hidden layer. A boundary that appears sharp on seismic profiles is in reality a wide, complex region, with gradients of temperature composition and water content. The rocks here are entirely solid, yet the presence of bound water can make them deform more easily, as though the mineral lattice itself is subtly loosened by the invisible presence of hydrogen. The transition zone can act both as a barrier and as a passage. Some mantle plumes may stall at its base, spreading laterally until they find a way upward, while some subducting slabs may flatten within it before sinking further into the lower mantle. The quiet mystery is how much of the planet's water cycle is tied to this depth. If the transition zone indeed holds several times the amount of water present on the surface, then deep Earth may play a far greater role in long-term ocean volume and climate regulation than surface processes alone. Whether this deep water is cycled actively with the surface or has remained trapped since the planet's formation remains uncertain. Another uncertainty lies in the effect of these phase transitions on mantle convection. The increase in density that occurs when olivine changes to wadsleyite and then ringwoodite can slow the descent of cold slabs, while the reverse transformation in rising plumes can release latent heat and influence buoyancy. These interactions may help shape the large-scale pattern of mantle flow, yet the precise details are difficult to resolve. A gentle analogy brings this layer closer to mind. The transition zone is like a middle floor in a vast building, where the ceiling and the floor are made of the same material but under different stresses causing them to deform in different ways. Here, rocks adapt their internal architecture without changing their overall composition, shifting atoms into tighter arrangements as the weight above increases. In some places, seismic studies have revealed anomalies within the transition zone regions of unusually slow or fast wave speeds that may correspond to pockets of partial melt or areas of differing composition. These heterogeneities could be remnants of ancient tectonic processes such as the accumulation of subducted material, or they could be related to ongoing interactions with mantle plumes. The transition zone may also influence the distribution of trace elements and volatiles in the mantle, acting as a chemical filter between the upper and lower layers. Over geological time, the cycling of material through this zone could alter the composition of magmas reaching the surface, linking deep processes to the history of volcanism and plate tectonics. The role of the transition zone in global dynamics is not passive. By modulating the movement of slabs and plumes, it shapes the exchange of heat and material between the upper and lower mantle, which in turn affects surface geology and climate. The depth and density changes associated with its boundaries can reflect seismic waves in ways that create complex patterns, requiring careful interpretation to distinguish them from other features. Advances in high-pressure mineral physics have deepened our understanding of this layer, yet direct sampling is impossible, leaving models dependent on indirect evidence. The minerals wadsleyite and ringwoodite are stable only at these depths, breaking down into other phases if brought closer to the surface. The few samples identified on Earth have come from unusual meteorites, or from inclusions in diamonds thought to have formed deep within the mantle. These tiny fragments provide rare confirmation of the mineral structures predicted by experiments and theory. In the stillness of deep time, the transition zone acts as a vast buffer between two great domains of the mantle, a place where rising and sinking currents pause, where minerals change their form but not their essence, and where water hidden in crystal lattices waits without flowing. As the descent continues, the path leads toward the greater pressures of the lower mantle, leaving behind a layer that holds in its silent mineral bonds a secret ocean locked away from the light. The lower mantle extends from the base of the transition zone at about 660 kilometers down to roughly 2,900 kilometers, a realm where pressure climbs above 130 gigapascals and temperatures approach 4,000 degrees Celsius. Here the mineral assemblage shifts again. Ringwoodite and wadsleyite transform into bridgmanite, a high-pressure form of magnesium, silicate perovskite, and ferropericlase, a magnesium iron oxide. Bridgmanite is the most abundant mineral on Earth by volume, yet it does not exist at the surface. It reverts to other forms when pressure drops. These minerals pack atoms more tightly than those of the upper mantle, making the lower mantle denser and stiffer, yet it still flows over geological time. Convection in this region is slower than in the upper mantle, and it may be organized into broad sluggish cells that transport heat from the deep interior toward the transition zone. A lesser-known detail is that seismic waves traveling through the lower mantle reveal subtle heterogeneities patches where velocity is slightly faster or slower than average, that may represent differences in temperature composition or even ancient slabs and plumes that have sunk or risen into this domain. Some subducted plates appear to plunge straight through the transition zone into the lower mantle, cooling their surroundings and affecting the flow pattern, while others flatten above the boundary, their fate determined by density contrasts and thermal structure. Soft ironies emerge in this deep environment. The minerals here are unimaginably strong by human standards, yet over millions of years they deform and flow like thick tar. The most common mineral on Earth is invisible to the human eye in its natural state, existing only under pressures no surface laboratory can replicate for long. The lower mantle is far removed from the surface, yet its slow movements influence the pattern of volcanoes, earthquakes, and continents above. The quiet mystery lies in how exactly the lower mantle circulates. Some models suggest that it mixes freely with the upper mantle, creating whole mantle convection that stirs the planet's interior as one system. Others argue for layered convection, where the transition zone acts as a partial barrier, slowing exchange between upper and lower layers. Geochemical evidence from volcanic rocks offers conflicting clues. Some magmas carry isotopic signatures that seem to come from deep, isolated reservoirs, while others suggest thorough mixing over time. Resolving this question is critical to understanding the thermal and chemical evolution of the planet. Another uncertainty concerns the composition of the lower mantle. While bridgemanite and ferropericlase are dominant, the proportion of each and the presence of trace phases like calcium silicate perovskite can affect density, seismic properties, and heat flow. Even small differences in composition can influence convection patterns over billions of years. A gentle analogy for the lower mantle is an immense, slowly turning gear in the machinery of the planet, meshing with the upper mantle above and the outer core below. Its teeth are made of crystals that resist change, yet they shift position under the steady push of heat and gravity. Just as a large gear moves more slowly but drives significant force, the lower mantle turns with less obvious speed, yet carries the bulk of the planet's internal circulation. Seismic tomography has revealed two massive structures within the lower mantle called large low shear velocity provinces, one beneath Africa and the other beneath the Pacific Ocean. These features extend thousands of kilometers across and rise hundreds of kilometers above the core mantle boundary. Their nature remains uncertain. They may be hotter than surrounding mantle, compositionally distinct, or both. Some scientists think they are remnants of subducted material that accumulated over time. Others see them as primordial features from Earth's earliest differentiation. These provinces may influence the initiation and location of mantle plumes, acting as anchors for deep upwellings that feed surface hotspots. Heat transport in the lower mantle occurs mainly by solid-state convection, but radiation may play a minor role at its deepest levels where temperatures are highest. The flow here is influenced by the high viscosity of bridgemanite, which resists deformation but can creep under sustained stress. Over long timescales, even this slow movement is enough to redistribute heat-drive chemical exchange and reshape the planet's deep structure. The lower mantle also plays a role in the core's cooling. Heat leaving the core must pass through the core mantle boundary and into the base of the lower mantle where it is carried upward. The efficiency of this heat transfer affects the vigor of convection in the liquid outer core, and thus the strength of the geomagnetic field. Variations in heat flux at the core mantle boundary can influence the patterns of convection in both layers, linking deep mantle dynamics to the behavior of the magnetic field. Rare glimpses into the lower mantle's mineralogy come from inclusions in super-deep diamonds, which can contain high-pressure forms like bridgemanite or ferropericlase preserved by the diamond's rigid structure. These inclusions provide direct evidence of the mineral phases predicted by experiments, though their small size and unusual origins mean they offer only partial insights. In this deep environment, every process moves on scales of time and space that dwarf human perception. A slab descending from the surface may take tens of millions of years to reach the core mantle boundary, cooling as it goes and altering the flow around it. A plume rising from the boundary may take equally long to reach the surface, carrying heat and material from depths few can imagine. Yet the balance of these motions shapes the planet's surface environment, influencing everything from the position of continents to the chemistry of the oceans. The lower mantle is the silent foundation beneath all geological change, a vast unseen engine that turns slowly but never stops. Its currents and structures are carved in a medium that is solid, yet in constant motion, a paradox that defines much of Earth's interior. As the journey downward continues, the path leads to the very base of the mantle, where rock meets metal, and the conditions change again, marking the threshold to the outer core. Here the slow, solid flow of silicate minerals gives way to the churning liquid motion of molten iron, and the planet's magnetic heart begins. The edge of the core is a boundary of extremes, the core mantle boundary, lying nearly 2,900 kilometers beneath the surface, where the solid silicate rock of the lower mantle meets the liquid metal of the outer core. This interface is marked by an abrupt drop in seismic wave velocities, shear waves which require a solid medium vanish entirely as they encounter the molten iron alloy of the outer core, while compressional waves slow sharply before speeding again in the denser fluid. Temperatures here may reach 4,000 degrees Celsius or more, and pressures climb to over 135 gigapascals. The contrast in composition is stark. Above is magnesium silicate bridgemanite and ferropericlase. Below is an iron-nickel alloy mixed with lighter elements such as sulfur, oxygen, carbon-hydrogen, and possibly silicon. A lesser-known detail is the existence of ultra-low velocity zones in patches along this boundary regions, tens to hundreds of kilometers across, where seismic waves slow dramatically, suggesting the presence of partially molten rock or chemically distinct material. These zones may be accumulations of subducted oceanic crust that has melted and pooled, or they may be areas where heat from the core has caused localized melting of the lowermost mantle. They are thought to be important sources for mantle plumes channeling heat and material upward. Soft ironies abound at this depth. The very base of the mantle, though solid, may behave in some ways like a fluid, as it creeps and deforms under immense heat, while the outer core beneath the liquid can sustain powerful currents capable of generating the planet's magnetic field. This boundary is both a barrier and a conduit, preventing direct mixing of rock and metal, yet enabling the transfer of heat and possibly trace elements between them. The quiet mystery lies in the composition and dynamics of this thin but influential layer. Some models suggest the lowermost mantle contains post-perovskite, a high-pressure phase of bridgemanite that forms only under the extreme conditions near the boundary. This mineral has markedly different properties from bridgemanite, including anisotropic seismic behavior and higher thermal conductivity, which could influence how heat escapes from the core. Yet the extent and distribution of post-perovskite remain uncertain, as laboratory experiments and seismic observations have not fully converged. Another unresolved question is the origin of the large low-shear velocity provinces that rise from the boundary beneath Africa and the Pacific. Whether these structures are long-lived and compositionally distinct or simply thermally anomalous regions of the mantle is still debated. A gentle analogy helps to frame this place. The core mantle boundary is like the shoreline of a vast hidden ocean, with the solid mantle as the land and the molten outer core as the sea. The shoreline is irregular, with bays, peninsulas, and deltas of molten and solid material interlocking, and currents from the sea influencing the weather of the land above. Here the weather is mantle convection, and the currents are the flows in the outer core. Heat transfer across this boundary is a driving force for both. Where heat flux is high, the outer core cools more rapidly, fueling stronger convection and a more vigorous magnetic field. Where heat flux is low, the outer core may convect less vigorously, potentially altering the magnetic field strength and stability. Seismic studies have begun to map variations in heat flux along the boundary using differences in wave speeds and attenuation. These variations may be linked to surface features such as hotspots, suggesting a deep connection between core dynamics and surface volcanism. The boundary also acts as a filter for chemical exchange. While large-scale mixing of rock and metal is improbable under current conditions, trace elements may diffuse across the interface, and reactions between the molten core and solid mantle could alter the composition of both over long timescales. Such exchanges may have been more significant in Earth's early history when the core was hotter and the mantle more molten. Ultra-low velocity zones provide further intrigue. Some are located directly beneath known hotspots, leading to the hypothesis that they serve as plume routes. Others occur far from any surface volcanic activity, hinting at processes unrelated to plumes, such as the accumulation of dense recycled material that remains trapped. Their small scale relative to the mantle as a whole makes them difficult to study, and their internal structure remains a matter of speculation. The post-perovskite layer, if widespread, could explain some seismic observations of strong anisotropy and sharp boundaries at the base of the mantle. This phase change may also enhance heat flow from the core, influencing the thermal evolution of the planet. The interplay of mineral physics, thermal gradients, and compositional variations creates a dynamic boundary that is far from uniform. In the stillness of deep time, the core mantle boundary is a shifting mosaic of heat, motion, and structure, where the solid Earth above and the liquid Earth below meet without merging. It is the interface between two great engines, the slow-turning convection of the mantle and the rapid churning flow of the outer core. As the descent passes through this threshold, the silicate framework that has carried the journey thus far gives way to the metallic heart of the planet, a realm of fluid iron whose motion sustains the magnetic shield that stretches far into space. This is the gateway to the core where rock yields to metal, and the story of the Earth's inner workings enters a new and molten chapter. The sea of liquid metal that forms the outer core stretches from the core mantle boundary down to about 5,150 kilometers beneath the surface, a vast spherical shell of molten iron alloy mixed with nickel and lighter elements, such as sulfur, oxygen, carbon, and possibly hydrogen and silicon. Here the pressure ranges from around 135 gigapascals at the top to over 300 gigapascals near the base, and temperatures may exceed 4,000 to 6,000 degrees Celsius. In this extreme environment, the iron-nickel mixture remains liquid because the temperature is above the melting point at these pressures. The outer core is in constant motion with convection driven by two sources: the release of heat from the core into the mantle and the compositional buoyancy created as the solid inner core grows, expelling lighter elements into the surrounding fluid. These motions occur on scales of hundreds to thousands of kilometers and at speeds of millimeters to tens of millimeters per second. Rapid compared to the creep of mantle rock, yet still imperceptible to human senses. A lesser-known detail is that the electrical conductivity of the outer core is extraordinarily high, allowing it to act as the medium for the geodynamo, a self-sustaining process in which the movement of the conducting fluid generates Earth's magnetic field. This magnetic field extends far into space, forming the magnetosphere that shields the surface from much of the charged particle radiation streaming from the sun. Soft ironies define this layer. The molten metal that humans forge in furnaces on the surface moves freely here without containment, yet its motion is orderly enough to produce a stable magnetic field over millions of years. The outer core is entirely invisible to direct observation, yet its influence is felt daily in the way compasses point and auroras dance near the poles. The very fluidity that gives it life also makes it impossible to support shear waves, so seismology knows it only through compressional waves and their reflections. The quiet mystery lies in the detailed structure of its flow. The geodynamo requires complex patterns of motion, including helical flows and rotational alignment, but the exact geometry and variability of these flows remain uncertain, Observations of the magnetic field at the surface combined with numerical simulations suggest that the outer core may host long-term circulation patterns, localized jets and swirling eddies, yet their arrangement changes over decades to centuries. Another uncertainty is the precise composition of the outer core. While iron and nickel dominate the identity and proportions of the lighter elements, influence density, melting temperature and convection. These lighter elements also carry clues to Earth's accretion and differentiation, yet they cannot be sampled directly. High-pressure experiments and theoretical models provide candidate mixtures, but no single model satisfies all seismic density and geochemical constraints. A gentle analogy for the outer core is a planetary-scale lava lamp, where heat from below drives rising plumes of lighter fluid and cooler material sinks mixing in complex patterns. Unlike the coloured wax in a glass globe, the outer core's fluid is opaque and metallic, its currents invisible except through their magnetic imprint. This imprint changes subtly over time. Magnetic north drifts, field strength fluctuates, and occasionally the entire polarity reverses. These reversals, recorded in rocks at the surface, indicate that the outer core's flow can reorganize in ways that temporarily weaken the global field before rebuilding it in the opposite orientation. The energy driving the outer core's motion comes not only from thermal convection, but also from compositional convection as the inner core crystallizes. When iron solidifies onto the inner core, it leaves behind lighter elements in the surrounding fluid, creating buoyant plumes that rise toward the top of the outer core. The balance between these two driving forces may have shifted over Earth's history, influencing the strength and stability of the magnetic field. The top of the outer core interacts with the lowermost mantle, where variations in heat flux can affect local flow patterns. Regions of higher heat flux may correspond to stronger upwellings in the outer core, while lower heat flux may suppress convection. This coupling could explain why certain areas of the magnetic field appear more stable or more active than others. Seismic studies have detected fine-scale structures at the top of the outer core, including possible stratified layers where mixing is reduced. Such layers might form if chemical composition varies with depth, or if heat flux is too low to drive vigorous convection near the boundary. A stably stratified layer could alter how magnetic field lines connect to the mantle, and might even help explain anomalies in the observed field. At the base of the outer core, where it meets the solid inner core flow, is influenced by the shape and growth of the inner core's surface. Irregularities in this growth can create asymmetric patterns in convection, potentially affecting the symmetry of the magnetic field. This link between the inner and outer core is a dynamic feedback system with changes in one influencing the other over timescales from decades to millions of years. The outer core's influence extends far beyond the deep Earth. The magnetic field it generates deflects most of the solar wind, shaping a protective bubble that helps preserve the atmosphere. Without this shield, charged particles from the Sun could erode the atmosphere over geological timescales, as is thought to have happened on Mars after its dynamo shut down. On shorter timescales, fluctuations in the field can affect navigation systems, satellites, and electrical grids, tying human technology to the hidden flow of liquid metal far below. In the stillness of geological time, the outer core is not still at all. It is a restless ocean of molten alloy, its currents weaving the planet's magnetic shield and carrying heat from the heart of the Earth toward the mantle above. Its boundaries connect two contrasting worlds, the silicate mantle solid but slow-flowing, and the solid inner core rigid yet growing within this sea. As the descent continues, the path will leave the fluid realm and cross into the inner sphere where iron crystals are locked in place, a silent heart at the center of the planet. A magnetic heartbeat pulses through the planet, born from the restless motion of the outer core. The geodynamo operates as a self-sustaining cycle. Moving liquid iron alloy conducts electricity. The flow of this conductive fluid generates magnetic fields, and those magnetic fields in turn influence the motion of the fluid. This feedback loop is driven by convection currents rising and sinking within the outer core, twisted into helices by Earth's rotation through the Coriolis effect. The result is a predominantly dipolar magnetic field with lines of force emerging near one pole and re-entering near the other, extending outward into space to form the magnetosphere. A lesser-known detail is that this dipolar structure is not perfect. Smaller-scale features create local magnetic highs and lows, and the field contains a non-dipolar component that drifts and changes on timescales of years to centuries. The field is constantly evolving in a process called secular variation, with magnetic north wandering unpredictably, and the strength of the field rising or falling in different regions. Soft ironies shape the story of this heartbeat. The invisible shield that has helped life flourish on the surface is powered by processes deep within a molten metal layer that no human will ever reach. The same flow patterns that sustain the field can under certain circumstances disrupt it enough to cause a reversal where north and south poles exchange places. These reversals have occurred irregularly sometimes with tens of millions of years between them, other times separated by less than a million. The quiet mystery lies in why reversals happen when they do. Simulations of the geodynamo suggest that changes in flow symmetry, fluctuations in heat flux at the core mantle boundary, or variations in the growth of the inner core could destabilize the field, but there is no complete predictive model. Another uncertainty concerns whether the field has maintained its current strength throughout geological history, or has weakened significantly at times. Rock records show that the average field strength has varied, and some intervals appear to have had much weaker magnetism, potentially leaving the atmosphere more vulnerable to solar wind. A gentle analogy frames the geodynamo as a colossal, slow-turning engine, whose pistons are columns of swirling liquid metal, whose fuel is the combined energy of cooling crystallization and chemical separation, and whose output is a planet-wide shield. Unlike any mechanical engine, however, its moving parts are fluid, its timing is irregular, and its lifetime is measured in billions of years. Evidence of the magnetic field's history comes from paleomagnetism, the study of the remanent magnetization locked into rocks as they cool from molten lava or are deposited as sediments. The seafloor preserves symmetrical stripes of alternating polarity on either side of mid-ocean ridges, a record of reversals stretching back hundreds of millions of years. Ancient continental rocks preserve even older signals, some more than 3 billion years old, showing that the magnetic field has been active for most of Earth's history. These records indicate that the field has persisted through massive impact supercontinent cycles and changes in atmospheric composition. At the surface, the magnetosphere shaped by the geodynamo interacts with the solar wind, a stream of charged particles emitted by the sun. Most of these particles are deflected around the planet, but some follow field lines into the polar regions, colliding with atoms in the upper atmosphere to produce the auroras. These shimmering lights are visible reminders of the connection between deep Earth processes and atmospheric phenomena. Without the magnetic field, the solar wind could gradually erode the upper atmosphere, stripping away lighter gases and altering climate over geological timescales. Mars, which lost its dynamo early in its history, offers a stark comparison. Its thin atmosphere and dry surface may be the result of this loss. The outer core's convective patterns that sustain the dynamo are influenced by the structure of the lowermost mantle. Heat flux variations at the core mantle boundary can modulate flow intensity, possibly creating preferred regions for upwellings and downwellings in the core fluid. Some of these regions correlate with long-lived anomalies in the surface magnetic field, hinting at stable deep structures guiding the flow. Yet even with these patterns, the field remains unpredictable on human timescales. Observations from satellites and observatories reveal accelerations, slowdowns, and regional changes that defy simple forecasting. Magnetic reversals leave clear signals in geological records, but unfold over thousands to tens of thousands of years, likely involving a complex rearrangement of the core's flow. During these transitions, the field may weaken to a fraction of its normal strength, allowing more solar and cosmic radiation to reach the surface. Though such events could have environmental effects, the fossil record shows no consistent correlation between reversals and mass extinctions, suggesting that the biosphere is resilient to these changes. Shorter-lived fluctuations called excursions also occur, where the field temporarily adopts a different orientation before returning to its previous state. These events are less well understood, but may be miniature versions of reversals triggered by localized instabilities in the flow. Technological impacts of field changes are more immediate. Rapid variations can affect satellite orbits, disrupt radio communication, and increase the vulnerability of power grids to geomagnetic storms. Understanding the geodynamo is therefore not only a matter of deep Earth science, but also of practical importance for modern infrastructure. In the stillness of deep time, the magnetic heartbeat has persisted through countless surface transformations from ice ages to warm greenhouse worlds, from the assembly of supercontinents to their breakup. It is a pulse without a sound, a constant weaving of invisible lines around the planet, shifting, bending, and sometimes reversing, but always returning. As the descent moves deeper into the core, the molten currents give way to a rigid center, the solid inner core where iron is locked into a crystalline lattice, growing slowly as the planet cools, and where the final secrets of Earth's heart lie, waiting. The hidden sphere at the center of the planet is the solid inner core, a roughly spherical body about 1,220 kilometers in radius, composed primarily of iron with a smaller amount of nickel and trace lighter elements. Pressures here exceed 360 gigapascals, and temperatures are estimated to approach or even exceed 5,500 degrees Celsius conditions, under which iron would normally be liquid. Yet the immense pressure forces the atoms into a rigid crystalline structure, locking them into a solid phase despite the heat. The inner core grows slowly over time as the planet cools with iron, crystallizing from the surrounding molten outer core and adding a thin layer each year, perhaps less than a millimeter. This crystallization releases latent heat, and also expels lighter elements into the liquid outer core, driving compositional convection and helping sustain the geodynamo. A lesser-known detail is that seismic waves travel through the inner core at different speeds, depending on their direction. They move faster along paths parallel to Earth's rotational axis than along equatorial paths. This property, known as seismic anisotropy, suggests that the iron crystals may be aligned in a preferred orientation, possibly hexagonal close-packed structures, stretched by the inner core's slow growth and deformation. Soft ironies define this place. The deepest, most inaccessible part of the planet is also the youngest major layer, having begun to form only after enough cooling allowed iron to solidify in the center. The solid heart of the Earth is locked in a lattice, yet it may rotate slightly faster than the mantle above it, slipping forward over decades in a slow and silent lead. The quiet mystery lies in the precise nature of its structure. Some studies suggest the inner core is divided into an outer shell and an innermost core with different crystal orientations, hinting at changes in growth patterns over geological time. Others propose that parts of the inner core may be less rigid or even partially molten, forming pockets where conditions approach the melting point despite the pressure. The cause of seismic anisotropy is also debated whether it is due to the alignment of crystals' variations in composition or dynamic processes such as differential rotation and internal convection within the solid itself. Another uncertainty is the age of the inner core. Estimates range widely from less than 500 million years to more than 1 billion, depending on assumptions about the thermal conductivity of core materials and the planet's cooling rate. If the younger age is correct, the geodynamo must have been powered largely by thermal convection alone for most of Earth's history, switching to a combination of thermal and compositional convection only after inner core nucleation began. A gentle analogy can help frame this hidden sphere. It is like a seed growing at the center of a fruit, forming slowly from the inside outward, its growth invisible yet shaping the entire organism. In this case, the seed strengthens the magnetic shield by providing a new source of energy to the dynamo, influencing conditions far beyond its solid surface. Seismic studies have revealed that the boundary between the inner and outer core, known as the inner core boundary, is sharp in some places and more diffuse in others. This suggests that growth is not uniform. Some regions may crystallize faster, while others accumulate a thin slurry of crystals before solidifying fully. The irregular growth could explain asymmetries in the magnetic field and variations in heat flow through the core mantle boundary above. The inner core's composition remains a matter of research. While iron dominates lighter elements such as carbon, hydrogen, oxygen, and silicon may be incorporated into its lattice in small amounts, affecting its density and seismic properties. The exact mix could offer clues to the materials that built the Earth and the processes that separated metal from rock during planetary formation. The inner core may also record a deep-time history of the magnetic field. If crystals grow in alignment with the prevailing field direction, their orientation could preserve a record of field changes over millions of years. Though retrieving such information is far beyond current technology, the notion that the inner core rotates at a slightly different speed from the mantle known as superrotation comes from subtle changes in seismic wave travel times over decades. Some studies suggest the rotation rate may vary, sometimes matching the mantle's rotation, sometimes moving slightly ahead or behind, possibly in response to changes in the flow of the outer core. Whether this motion is steady or oscillatory is still debated. In the stillness of deep time, the inner core is not entirely still. It grows, shifts, and perhaps turns imperceptibly a silent partner to the molten currents that surround it. Its formation marks a turning point in the planet's evolution, altering the balance of energy, driving the geodynamo and influencing the magnetic field that reaches into space. This small sphere, compared to the size of the planet, holds the densest and most extreme matter accessible to direct study through natural experiments of seismic waves and mineral physics. As the journey inward reaches the center, there is no further to go in depth. But the questions only multiply: how the inner core began, how it will change as the planet cools, and how its slow growth continues to shape the surface world far above. Here at the very heart of Earth, motion and stillness coexist, and time is measured in the accretion of atoms onto a crystalline lattice that will remain long after the surface landscapes have been erased and remade many times over. Anisotropy in silence marks one of the most intriguing features of the inner core. Seismic waves crossing it reveal that compressional waves travel faster along the planet's rotation axis than along paths near the equator, a pattern first recognized in the late 20th century and now confirmed in numerous studies. This directional difference in wave speed is subtle, measured in just a few percent, but consistent enough to suggest that the iron crystals are not randomly oriented. Instead, they may be aligned by processes related to the growth of the inner core, its deformation by surrounding flows, or even by convective motion within the solid itself. The dominant crystal structure under these pressures and temperatures is thought to be hexagonal, close-packed iron, whose elongated C-axis can produce anisotropy if the crystals share a common alignment. A lesser-known detail is that the degree of anisotropy appears to vary with depth, with the innermost region showing different characteristics from the outer part of the inner core. Some researchers interpret this as evidence for two distinct growth phases: an earlier phase that produced the innermost core with one preferred orientation, and a later phase that built the outer portion with another. Soft ironies are embedded in this arrangement. The most rigid layer of the planet may have its internal structure shaped by flows in the liquid metal surrounding it. The solid core, often described as a static heart, may itself experience slow circulation of material, with crystals dissolving and reforming over millions of years. The quiet mystery lies in how such alignment develops and persists. If the inner core rotates at a rate different from the mantle, even by fractions of a degree per year, then its surface would move relative to the flow of the outer core, potentially creating zones of faster growth on one side and slower growth on the other. These asymmetries could generate stresses that align crystals in consistent directions. Another possibility is that variations in temperature and composition at the inner core boundary guide the orientation of newly formed crystals, imprinting a record of outer core convection patterns. Seismic data also hint at hemispherical differences in wave speeds, with one half of the inner core allowing faster travel than the other. This could reflect differences in crystal size alignment, or even impurity content, possibly linked to uneven growth or melting at the boundary. The hemispheres appear to be offset from the rotational axis, suggesting that the controlling factors are dynamic rather than purely geometric. A gentle analogy can help picture this arrangement. The inner core is like a tree trunk with growth rings that are not perfectly circular, their thickness varying with direction, and with the grain of the wood tilted and stretched by forces from outside. Just as dendrochronologists read a tree's rings for climate history, seismologists read the travel times of waves through the inner core to infer patterns of growth alignment and change. The anisotropy also affects how waves scatter, with some paths producing clearer signals than others, offering further clues about the distribution of crystal orientations. Laboratory experiments on iron and iron alloys under high pressure support the idea that deformation can cause alignment, but reproducing the exact conditions of the inner core remains challenging. Computational models simulate crystal growth under anisotropic conditions, exploring how small-scale processes could yield the large-scale patterns observed. These models suggest that even slow, steady stresses from the surrounding outer core could gradually align crystals over millions of years, especially if the inner core experiences differential rotation. The anisotropy may also evolve over time. If the growth of the inner core accelerates or slows in response to changes in heat flow from the core to the mantle, then the pattern of alignment could shift, leaving behind layers of differing texture. Such changes might eventually be detectable in long-term seismic records, though the timescales are beyond human lifetimes. Another open question is whether convection occurs within the solid inner core. While it is rigid, temperature and compositional gradients could create buoyancy forces capable of driving extremely slow solid-state flow. If such convection exists, it could redistribute crystals and alter anisotropy, adding another layer of complexity to the seismic record. The interaction between anisotropy and the geodynamo is indirect but important. The pattern of crystal alignment may reflect the geometry of outer core convection, which in turn shapes the magnetic field. If the inner core's growth influences where and how heat leaves the outer core, then changes in anisotropy could correspond to changes in magnetic field behavior over geological time. Yet without a direct way to sample the inner core, these links remain speculative, supported only by the convergence of seismic, experimental and modeling evidence. In the stillness of deep time, the anisotropy of the inner core is both a snapshot and a motion picture fixed in its crystalline lattice, yet slowly altered by growth stress and perhaps circulation. It is a structural fingerprint of processes at the very center of the Earth, recorded in the invisible paths of seismic waves and interpreted through the patient work of scientists piecing together a story from tremors that pass once and never return. As the descent narrative draws near its end, the focus will turn to the final stillness at the exact center, a point where motion ceases, where time is measured only by the slow accumulation of atoms, and where the journey into the planet's heart becomes a meditation on permanence within change. Stillness at the center is not the stillness of absence, but the stillness of completion, a place where every direction leads outward, and where the slow processes that shape the planet converge. The exact center of the Earth is a point in the solid inner core surrounded by crystalline iron, compressed beyond any surface experience, its atoms packed into an ordered lattice by the unyielding weight of the planet above. Here gravity pulls equally in all directions, cancelling itself to zero, so that the pressure holding the structure together comes entirely from the overlying layers, rather than from the downward pull of mass. Temperature is estimated to be close to that of the surface of the Sun, yet the pressure is so immense that the iron remains solid. A lesser-known detail is that seismic waves do not pass through this central region in ways that suggest perfect uniformity. Instead, subtle variations hint at differences in crystal size alignment or impurities even at the very core. These may be relics of the inner core's earliest growth preserved because nothing can erode or overwrite them once locked in place. Soft ironies define this absolute depth. The deepest and most extreme environment in the planet is also the most isolated, separated from the surface by thousands of kilometers of solid and liquid layers, yet its existence is essential to life above. The rigid stillness here is the foundation for the motion in the outer core that sustains the magnetic field, the shield that has helped keep Earth's atmosphere and oceans intact for billions of years. The quiet mystery lies in the inner history of this place. The central point may be the oldest part of the inner core, its atoms having joined the lattice hundreds of millions or perhaps more than 1 billion years ago, yet the exact age remains uncertain. It is possible that the very center formed under different conditions than prevail today, with the early inner core growing in a smaller, hotter planet and surrounded by a younger outer core flow pattern. If so, its crystalline structure could be subtly different from the layers above it. Another unresolved question is whether the center marks a boundary in composition. If lighter elements were excluded from the earliest solidification, the innermost region might be slightly purer iron than the rest, affecting density and seismic behavior. A gentle analogy helps to imagine this hidden heart. It is like the kernel of a seed so deeply enclosed that nothing from outside reaches it directly, yet its formation changes the entire growth of the structure around it. The kernel itself is not active in the way the surrounding layers are, yet it is the point from which their arrangement is defined. At the very center, no convection can occur. There is nowhere for material to move. Instead, atoms are added in place as iron crystallizes from the liquid outer core and attaches to the existing lattice. Growth at the center is the slowest anywhere in the planet, a motion measured in fractions of millimeters per year, invisible on human timescales yet significant over geological epochs. The symmetry of this point is absolute in geometry, but imperfect in material. Seismic observations suggest that the inner core's texture is not completely uniform, with zones that scatter waves more than others, and regions that appear to transmit them slightly faster or slower. These differences may be the result of uneven growth or varying impurity content over time. If the inner core's rotation rate changes relative to the mantle even slightly, The center would slowly experience different orientations of stress from the surrounding flow, potentially imprinting minute structural differences that persist indefinitely. This central stillness is not immune to the planet's history. Variations in outer core convection, shifts in mantle heat flow, and even the rearrangement of continents can indirectly affect how the inner core grows and cools, altering the way atoms arrive at the center. Over hundreds of millions of years, these influences may leave patterns like the annual rings of a tree, not in visible layers, but in the alignment of crystals and the distribution of trace elements. In a world where the surface is constantly remade by erosion, volcanism, and tectonics, the center changes so slowly that it becomes the closest thing to permanence the planet possesses. And yet permanence here is only relative. Given enough time, the inner core will eventually grow outward until it consumes the outer core entirely, ending the convection that drives the magnetic field. In billions of years, the whole core may solidify, leaving the Earth geologically quiet, its shield against the solar wind gone, its atmosphere and oceans vulnerable. The journey to the center is therefore also a journey forward in time to a future when this stillness will expand outward and the planet will pass into a different phase of its existence. For now, however, the center remains a point of balance, holding the record of its own formation and the subtle marks of every change in the deep interior since then. It is silent because sound waves here are trapped within iron that transmits them without echo. It is still because every movement of matter around it begins and ends beyond its reach. In the vast chronology of the Earth, it is a constant, yet one that exists only because of continuous change above it. The surrounding layers feed it with atoms, press it into crystalline order, and insulate it from direct contact with the outer world. At the center, all lines of descent converge. The crust with its shifting plates is a distant boundary. The mantle with its slow currents is a distant engine. The outer core with its churning metal is a distant sea. Here those motions are felt only as the slow ticking of growth, the addition of a layer invisible but inevitable. In this way, the stillness at the center is not an absence of activity, but the distilled outcome of all activity, a resting place for atoms that have travelled from the surface through subduction, through the mantle into the core, and finally into the tightest possible embrace of pressure. The journey inward ends in this place of quiet density, where the iron lattice holds against heat and time, and where the shape of the planet is decided at an atomic scale. From here, every step outward is a return to motion, to change, and to the dynamic life of a planet that has been shaped from the inside for more than 4 billion years. The center of the Earth holds its silence, yet the warmth from its birth still moves outward through the solid iron lattice, through the molten metal sea, through the vast and heavy mantle, and into the thin crust where light and air begin. Every layer above carries a slower rhythm than the one beneath it, each passing on its motion, its heat, and its record of time. Rising from the center is like retracing a story in reverse, the stillness giving way to slow currents, the slow currents to shifting plates, and the shifting plates to wind and water shaping the surface. Yet in this final moment there is no need to return. The mind can remain here where gravity balances perfectly in all directions, where there is no up or down, no surface or horizon, only the weightless press of iron holding against its own heat. The crystals are fixed in place yet slowly growing, adding atoms one by one in a process too slow for measure, like dust settling in a room no one enters. Outside, continents drift and oceans open, but none of that reaches here. The temperature stays constant, the pressure absolute, the darkness complete. If there is movement, it is measured in centuries in the alignment of crystals, or the faint rotation of the whole sphere within its molten shell. In this stillness there is no sound but the imagined hum of atoms locked in their lattice, no light but the unseen glow of heat held under crushing weight. Time stretches, the sense of scale dissolves, and what is left is the enduring calm of the Earth's deepest place. Here in the quiet heart of the planet, all motion is absorbed, all noise is stilled, and the long story of the interior rests in perfect balance.